There's a reason for it.
So moving from a brand new emerging market to a more mature commodity and area, but nevertheless important from a recycling point of view, I'm delighted to introduce Vladimir Sedivy to talk about recycling salt and when does it make sense.
When does it make sense? Yes. I'm president of Salt Partners, and we are participating regularly at the European Union salt meetings. And there was one about 5 years ago in Brussels, and we were presented the concepts of the Commission about circular economy, about recycling, and that was done purely from the bureaucratic viewpoint of the people working at the Commission, without any respect to what actually is salt and what is sodium chloride. And when I was listening to it, I was asking myself, yes, well, all right, it sounds so nice, but does it make sense? And that brought me to the idea to make a presentation and to write a paper on salt recycling. When does it make sense? I have a question to you. Who knows how much salt we have in the world? What would be the layer of salt if the climate change goes on and all the water evaporates? What would be the thickness of the layer at the bottom of the sea? Who would like to take a guess? Thomas? 1 kilometer. Okay, anyone else? Anyone else would like to take a guess?
2 kilometers.
Not that much, no. Only about 35 meters. Now, the proof would be that you think, okay, we have 3% of salt in seawater, and the layer of seawater is on average 4 kilometers. So 3% from 4,000 meters is 120 meters, but the density of salt is double of the water, so it would be about half of that, so around 50 meters, 50 meters, depending on how you take the figures, how precisely you take them. 40 meters of salt. One very important recycle of salt is the movement of the seawater. The seawater, wherever you start, perhaps somewhere in the Gulf Stream, passing by England, to the north, cooling down and flowing through the Atlantic back to the southern part of the world, and rising, getting warmed up in the Indian Ocean and in the Pacific, and then returning back around the Cape of Good Hope back to the Atlantic. Now, this cycle is very slow. It takes about 1,000 years for the water to recycle, but considering that the Earth is 4 billion years old, and we have water on the Earth for most of that time, it has recycled many, many times. And this is the reason why the composition of the seawater everywhere in the world is the same. Somewhere it is more diluted, somewhere it is more concentrated, but the composition is the same. Then we have another cycle, we have another recycling, and this is the rock cycle. Most of the rocks, or all of the rocks, actually start with the absorption of carbon dioxide by the calcium present in the seawater, forming calcium carbonate, which then settles at the bottom of the sea as a dust, mud, and proceeds slowly to the deeper parts of the crust until they modify, they cement, they melt, and somewhere again this crust rises up and comes from the surface of the earth as a rock. Of course, the rock can weather, or it does weather. It is subject to heat and cool and temperature changes, and water effects, carbon dioxide dissolved in the water, and so on and so on. So it weathers. It also weathers by the action of plants and fungi and algae. And finally, the water cycle consists of evaporation of water from the sea and from transpiration of the plants and getting moved towards the higher areas of the earth where it is cooler, it condenses, falls down as rain, and returns on the surface of the earth, but also underneath the surface back to the sea. So the salt, of course, is a part of the circuit. The salt is present in the rocks. All rocks are salty, and this is how it returns back to the sea. What is the quantity of this salt that is being recycled? It's about 4 billion tons per annum. 4 billion tons per annum compares with the quantity of salt that is being produced worldwide, which is around 350 million tons per annum. So only about 1/12, 1/13 of all the salt that is recycled naturally is actually being produced. And what is the salt being used for? Mostly by the chemical industry for production of caustic and chlorine for production of PVC, which of course is not soluble and is not really practically recyclable, for production of sodium carbonate. Sodium carbonate is used to produce glass. Glass is also not soluble and does not recycle. So only the salt for food, which is about 1/10 of the total salt produced, is being actually recycled. Whatever salt we take, we also discharge and it goes back. Whatever spaghetti we cook, the water goes back to the sea. So, of course, there is some road de-icing and so on. So only perhaps 40% of the salt that is being produced is actually recycled. So out of the 350 million, perhaps 100 million is being recycled. This is the calculation that is related to what I just said, 4% of the natural circulation. How much recycling of this salt, of this 350 million tons of salt that we are producing, how much of that to be recycled really in connection with the use of the salt makes sense? Well, one of the first criteria that we had to take a look at is the purity of the salt, is the quality of the salt. When I started in salt some 50 years ago, we were looking at 3 impurities in the salt, or perhaps 4, which was calcium, magnesium, sulfate, and insolubles. And nowadays, when we are testing salt for some use, whoever comes to us and says, well, look, I have salt, and I want to make salt for human consumption, or I want to make a salt for this and that, we say, all right, well, let's take a look at what is there in that salt, except for sodium chloride. And this is the list. It's a very, very long list. And for any use of salt, every one of these elements plays a role. Then there is the question of the cost and of the price of the salt. This curve shows that generally the price of the salt, cost of the salt, is a question of the purity. And the purity of the salt that is being produced and consumed starts at around 90% of purity and about $10 per ton. And it goes on and it rises up to $100 per ton of salt for good quality vacuum salt for electrolytical purposes. So there are huge differences in prices. Does it make sense to produce salt or recycle salt and compete with the new salt, new fresh produced salt, specific for the purpose? One of these applications that we are being confronted with on a weekly basis, getting inquiries, we have desalination plant and we have desalination reject. And we would like to, there's a lot of salt in it, and we would like to utilize the salt. Now, the reject has usually around 6, perhaps 7% concentration. We were looking in connection with this project into possibilities, into technologies that exist, and into the cost of these technologies, how to actually make salt. And these are the 6 or 7 technologies that we looked at, and we calculated the capital cost, operating cost, financing cost, possible price or selling price of the salt depending on the quality that can be used, that can be obtained. These were the 6 major offers that we had after evaluating about 15 various suppliers and their technologies and so on, comparing. And we have evaluated the profitability on the basis of that cost of steam and electricity and so on. And we have seen that there was only one that offered a reasonable return on investment. All the others, 6 to 8%, well, nobody would spend money on a large project to get only 6 or 7 or 8%, 9% return. This return on investment was quite unique. It was only due to the fact that the selling price of the salt was very high, was in a place that the salt was not available. And it was also due to the fact that this was a large industrial project with own power station, and there was a bleed of steam available from the turbine that they didn't know what to do with, condense it or recompress it and reuse it. So there was a steam that was actually available at negative cost. And therefore, there was a possibility to do it and to actually do it profitably. But that is unique, and we have so far not identified any other project where this would be possible to do profitably. There are cases where it makes sense, and one of the cases is the aluminium recycling, and this was a project that we did in the United States. There is a rotary smelting or remelting furnace heat it with natural gas, flame. When the aluminium is melted, it's poured out of the furnace. In the furnace, the molten aluminium at about 650 degree centigrade temperature is covered by a layer of salt. But the salt is not just sodium chloride. It is a mixture of potassium chloride and sodium chloride, and the eutectic mixture has a melting point just slightly above melting point of aluminium, and therefore it's lighter than aluminium, so it floats on the aluminium, and it prevents oxidation of the aluminium, at least partially. It consists then mainly of the salt, but also of some aluminium oxide and of some burnt color from the sugars from the cans from beer and Coca-Cola and so on and so on. It's an awful stuff. It's black and smelly. Here it is. Here it comes from the furnace, and here you can see it still contains quite a lot of aluminium. So, and it's hot. It has to cool down. Then there is the question of what to do with it. When it gets wet, it smells terribly. This is after cooling here. This is a cooler, this is a mill, and this is the cold raw material, and it's put in bags. And then there's a question what to do with it. When it gets wet, it smells terribly. It's a formation of ammoniac and other mercaptans and so on. Terrible, terrible thing. So it has to be kept dry. That means storage cost. At the time of this project, potassium chloride was selling at $700 a ton. Salt was selling at about $50, $60 a ton. So it was not the value of the salt, of the sodium chloride, it was the value of the potassium chloride that was driving this project. We signed a contract with the owners of this recycling company, and we offered our technology consisting of crushing, milling, screening, then desalting. That was the core technology from us, was the hydrosol technology for dissolving or leaching the salts out of the dross in such a way that at the bottom of the extraction equipment, the dross was salt-free, so that it could be sold, for example, as a cement additive. That was the reason why I was asking before. To get the liquid at the top of the extraction tower at the highest possible concentration, so that the recrystallization of this material afterwards would be from concentrated liquid, and therefore it would be economic. And then, of course, evaporation and crystallization of the flux of salts, drying, handling, packing, and hydrosol is a countercurrent process which is capable of doing this, salt-free at the bottom and concentrated salt at the top. And this is how the plant looked like. It was not a big plant, but it worked very well. It consisted of the hydro extraction. This is the collection of the brine. This is the evaporation and crystallization. Here is the filter for the desalted dross. This is the hydro extractor view from the floor. That's me during the startup checking the level of the dross in the hydro extractor. This is the filter. This is the brine. This is the evaporator crystallizer. That's how the recrystallized sodium chloride and potassium chloride comes out from the plant, and that's a picture we have taken after the commissioning of the plant and acceptance with the managing director in the middle, myself next to it, and the other people of the team. Acceptance certificate and conclusions. Now, when does it make sense to do recycling of salt? Certainly not if you cook spaghetti and if you want to evaporate the water to dryness and to reuse the salt. Definitely not. It makes sense if the brine is available at a high concentration, if solar concentration and crystallization is possible, because you know you need 650 kilocalories to evaporate 1 kilo of water. You only need 100 kilocalories to heat up water from 0 to 100. And then 6.5 times more to evaporate the water. And this is an awful lot of energy. And the only energy that we have available, more or less free of charge, is the solar energy. And solar evaporators, the ponds, are the most efficient collectors of solar radiation, environmental energy, assisted by the wind. There is no competition to that. Any other energy is less efficient. Thermal evaporation, if steam or power is very cheap. Membrane technologies, if steam is expensive, because membrane technologies require lots of energy, of power, to press the water through the membrane at pressures of 60 bar, or the high utilization membranes at 120 bar. It's an enormous pressure, enormous amount of energy that is needed. If salt is expensive, if brine is, and dilution of the discharge brine to the rivers is not possible, and if brine cannot be reused as such, for example, for water softening, you put a high concentration of brine into the ion exchanger and you get it back with just a little of calcium. So potentially you could reuse it. And if the brine does not contain impurities that limit salt marketability, which is the list of the elements that I was presenting before. Why not turn your salt into gold? Who knows how to turn salt into gold? Well, the one way is to take the coin that is on our display, and when you then come to Salt Partners for anything that has to do with salt, that coin is worth 1 troy ounce of gold, which is today about $1,900 if you come to us with an order for whatever. So please help yourself. And the other way is, as with anything, produce it cheaper and sell it more expensive. Thank you very much.
So thank you to everybody. Thank you very much to our sponsors. I have to give them a bit of a plug, El Martis, for sponsoring the lunch yesterday and today. And to Vladimir over there, thank you very much for supporting us again. Also, as Mike has just said, thanks to the speakers. It's a lot of work for you to prepare such fantastic presentations. So thanks to all of you for your time that you took to be here. Delegates, have to thank you too, especially this time. It was a bit of a problem getting here, so thanks. I think everybody actually made it on time, in spite of everything, so well done everybody. A big clap to everybody for making it here.